Longitudinal and transverse waves is our topic today. Recall from previous activities that longitudinal waves propagate in the same direction as the displacement of the transmitting field or medium. On the slinky, that's when you pushed and made pulses for a longitudinal wave. A transverse wave propagates in a direction perpendicular to the displacement of the transmitting field or medium. That's when you move the slinky back and forth to generate transverse waves. Let's focus first on longitudinal waves. Longitudinal waves are also called compression waves. That's because the part that you pushed together to make the pulse, the part of the slinky that's all squished together, is called the compression. The part of the slinky that's not squished together, that's more spread out, is called the rarefaction. Whether or not a wave is longitudinal or transverse is describing the direction of propagation of the wave pulse. Another way to talk about waves is based on the method of propagation. We're going to look at two types of waves, and these waves are based on how the waves propagate. First, mechanical waves. Mechanical waves require a medium to travel through. That means they have to travel through something. A solid, a liquid, a gas. They cannot travel through emptiness, which we might call empty space. Electromagnetic waves can travel through a medium, or they can travel through space, which we can also call a vacuum. Electromagnetic waves are created by electric and magnetic fields. You should have a copy of this diagram of the electromagnetic spectrum. Affix it into your composition book now. Notice what types of things are considered electromagnetic waves. We have radio waves, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. Those are all types of electromagnetic waves. This top diagram shows you the relative frequency, radio waves having the lowest frequency, all the way up to gamma rays with the highest frequency. Next, we have the relative wavelengths of electromagnetic waves shown up here, with radio waves having the longest wavelengths and gamma rays having the shortest wavelengths. Notice those exponents, 10 to the 6 all the way to 10 to the negative 18. That's quite a range. Below that, you have some diagrams that show you about how big these things are that we're talking about. 10 to the 6 would be about the size of Mount Everest. 1 meter would be about the size of a human. Down here around ultraviolet, those wavelengths are about the same size as a virus, and so on down the line. Notice in the middle of this diagram you have visible light. Well, all electromagnetic waves travel at the same speed as light, since light is part of the electromagnetic spectrum. The speed for all electromagnetic waves, including light, we use the letter C, and this is 3.0 times 10 to the 8th meters per second. That's the speed of all electromagnetic waves.
Right, we're going to do a quick demonstration with this buzzer. Okay, I have placed the bell jar over the buzzer. Notice you can still hear the buzzer. Now I'm going to turn the vacuum pump on. What's happening to the sound of the buzzer? Notice how much quieter the buzzer is now?
We already know that sound waves propagate as longitudinal waves. This demonstration shows us that sound waves are mechanical waves. They require a medium through which to travel. When the air was pumped out of the chamber, the sound waves got much softer because they did not have as much of a medium through which to travel. Now watch this simulation as I change the pitch and the volume of the sound waves and see what happens to the waves. What characteristic is changing as the volume is changed? What characteristic is changing as pitch is changed? Notice a change in pitch changes the frequency of the wave, and a change in volume changes the amplitude of the wave. Recall this diagram that shows the different characteristics of waves. This particular diagram is showing a transverse wave. Let's see how some of these characteristics show up on a longitudinal wave. Let's make this a little bit smaller, and let's move it up here out of the way. And now we can compare some of the wave characteristics for the transverse wave compared to the longitudinal wave. On the transverse wave, wavelength was measured from crest to crest, or from trough to trough. On the longitudinal wave, wavelength is measured from compression to compression. On the transverse wave, amplitude was how far the wave rises or falls from rest position. On a compression wave, amplitude is referred to as line density. That means how thick this compression is. This tells me the amplitude. If I have a higher amplitude wave, this compression will be much thicker. Consider the following 3 movie scenarios that involve waves and decide if they are realistic from a physics viewpoint. Write each of them in your composition book and explain your answers.